This is Ideas Worth Exploring by Mark MacDonald. Microwaves, X-rays, gamma rays, radio waves, ultraviolet, infrared. What do they have in common? They're all colors of light you can't see. Never thought of microwave as a color before? Well, I might be stretching the word color a little bit, but if you put light through a prism, it'll separate into the colors you're used to, but above the red light will be an invisible color called infrared. And above that are the microwaves, and above that would be the radio waves, except you'd have to have a ridiculously large prism to interact with radio waves at all, so never mind them. Below the violet light is the invisible color ultraviolet, and below that would be X-rays, like the kind used by the dentist, and below that would be gamma rays, like the kind that made the Hulk turn green. But X-rays and gamma rays would be very hard to separate using an ordinary prism, so don't try too hard. Today we're going to talk about light. What is light? And how do our eyes use it to see? And I'll also go over microwaves and X-rays and all the rest, because they're also light, kind of, sort of, in a way. Normal people use the word light to refer only to the stuff you can see, and the catch-all term that also includes the invisible stuff is electromagnetic radiation. But that's getting ahead of ourselves. First we're going to talk about vision and why Isaac Newton poked himself in the eye with a needle. Then we're going to go over electromagnetic radiation, the whole spectrum from radio to gamma rays. Finally, we're going to speed through some facts about light, including the answer to the age-old question, why is the sky blue instead of red or purple? And also a different but related question, why are plants green? We've known about light since the Dark Ages, but in the early days, many people thought that a person's eyes created light that would go out into the world and grab objects so you could see them. Or in other words, they thought that people shoot lasers from their eyes to be able to see. But my main man Aristotle thought that this was ridiculous and instead believed that the eye received rays of light instead of creating them. He ended up being right about that, but people would continue to argue about it for the next 2,000 years. Lots of people did lots of things with light in the meantime, but I'm going to focus on our boy Isaac Newton. He showed that when you shine pure white light through a glass prism, it gets separated into the colors of the rainbow. Newton wrote that there are 7 colors, red, orange, yellow, green, blue, indigo, violet, Roy G. Biv. But he cheated, because indigo really shouldn't be there. He thought there ought to be 7 colors in the rainbow, because there were 7 musical notes in an octave, and 7 planets known at the time, though that's planets with air quotes, because it included the sun and the moon. So Newton added indigo to make the number 7, even though it's very hard to tell the difference between indigo and violet in the rainbow. They're pretty much the same color. Also, the words we use for colors have changed since Newton's days, so what he called blue, we would call cyan, and what he called violet, we would call blue, as in the phrase, roses are red, violets are blue. But he decided to throw indigo into the rainbow, and ever since, school children have had to learn about a color that doesn't deserve the recognition. A more skeptical man than me might even suggest that he was paid by indigo to do some false advertising, but who am I to accuse Isaac Newton of such a thing? Another thing Newton did. You know the rhyme that children say when they promise they're telling the truth? Cross my heart and hope to die, stick a needle in my eye. Well, Newton took it literally and actually stuck a blunt needle in his eye socket. Not piercing his eye, but between the eyeball and the bone, so he could poke at the back of his eye. When he poked the bottom of his eye, he saw a bright spot at the top of his vision. When he poked the right side of his eye, he saw a bright spot on the left side of his vision. Through this, he learned that the eye captures images upside down and backwards. This is just like a camera. The image of a camera records on film is also upside down and backwards, and this has a simple explanation if you can see a diagram of it, but alas, I am unable to convey visual information using only my voice, so I guess you'll have to Google it, or just take my word for it and be impressed by how metal Newton was. On the topic of seeing upside down, many vision experts believe that human babies see upside down for a short time before their brain learns to flip the world right side up. We don't know for sure how soon this happens, but what we can do is make goggles that flip everything you see upside down to learn what it feels like. A man named George Stratton was the first to do this in the 1890s. He he found that after wearing the glasses for 4 or 5 days, things started to look right side up again. His brain had adapted and he could interact with the world just like he used to, though he said things never felt quite normal. However, in experiments that have tried to duplicate this original one, subjects generally say that they never feel like their vision flips. They still feel like they're walking on the ceiling, but they did become used to it after enough time, enough that they could act normally. So maybe Stratton lied, or maybe his brain was just special, but it's clear that the human brain is very good at adapting to changes in vision. Okay, we've talked enough about vision, but what about light? What is it? Is light made of atoms like you and me? Good guess, but actually no. With only a little bit of hand waving, I can say that light is actually a wave. Just like a wave of water carries energy from one place to another, light waves also carry energy. But while a water wave can only travel through water, a light wave can travel right through empty space. That's because light is a wave of electricity and magnetism, which we call electromagnetic radiation. And that's a very profound statement that took many years for scientists to fully grasp, so let's spend a minute to break it down. First, what does the electromagnetic part of electromagnetic radiation mean? It turns out that light is directly related to electric and magnetic fields, which you can think of as invisible webs that extend through space. A man named James Clerk Maxwell, JC to his friends, was the first one to show how light is related to electric and magnetic fields. First, it was well understood at the time that a charged particle, like an electron, creates an electric field. And when a charge moves, it creates a magnetic field. But JC also realized that when a magnetic field grows or shrinks, it creates an electric field. And when an electric field grows or shrinks, it creates a magnetic field, and so on in circles. So the electric and magnetic fields sort of chase each other across space. And they do this really quickly. In fact, they do it at the speed of light. That's because an electric and magnetic field chasing each other is exactly what we mean by an electromagnetic wave, or in other words, light. Light is just electric and magnetic fields chasing each other across space. Light is created whenever a charged particle moves, and light stops when it's absorbed by another charged particle, often an electron in an atom. When light is created, it tends to travel out in all directions. Another way to say travel out in all directions is the word radiate, kind of like the radius of a circle. So when we say that light is radiation, we just mean that it's a wave that carries energy through space out in all directions from its source. It doesn't mean that it's dangerous, like the radiation from a nuclear reaction. Marie Curie used the word radioactive to refer to her newly discovered polonium, but life would make much more sense if she'd chosen a different word, because most of the air quotes radiation that comes from a nuclear reaction is not the same creature at all as what we've been talking about today. Out of all the types of nuclear radiation, only one type, gamma rays, is an electromagnetic wave, while the rest, including alpha, beta, and neutron radiation, are completely different and have nothing to do with light. So when I say the word radiation, don't think nuclear. Think radio, or light ray, or radical new science thing you learned today. Okay, for this next part I need to talk some more about waves. The next time you see a slinky, grab the end and wiggle it up and down, and you'll see waves run across it. The distance between the top of two waves is called the wavelength. Yes, very original, I know. Light also has a wavelength that's defined in a similar way, but for wiggles in the electric and magnetic fields instead of wiggles in the slinky. The wavelength is important because your eyes see different wavelengths of light as different colors. Red light has a wavelength of about 700 nanometers, or slightly smaller than a bacteria. Violet light has a wavelength of about 380 nanometers, almost half the wavelength of red light. Smaller wavelengths, which means higher energy because the waves are coming closer together, get you ultraviolet light, which can give you a sunburn, and then X-rays, which pass right through your body and can be used to show a picture of your bones. A water molecule has a diameter of 1.5 nanometers, which is right between the shortest ultraviolet and the longest X-rays. Smaller than X-rays, you have gamma rays, which have a wavelength of less than 1 picometer, smaller than the smallest atom. It takes several feet of concrete to block gamma rays, so try to avoid standing right next to a nuclear bomb, particle accelerator, or lightning strike. On the other end of things, when you go to longer wavelengths than visible light, you get less energetic waves. Infrared light goes from about 1 micrometer, which is bacteria size, up to 1 millimeter, the size of a pencil point. About half of the sun's light that reaches Earth is in the infrared, and even though you can't see it, you can still feel it as heat. Your own body actually emits light in infrared because of a quantum thing caused by atoms vibrating. That's why night vision goggles can see your body heat, because you're like a candle emitting infrared light all the time. At longer wavelengths than infrared, you have microwaves. Microwaves are between 1 millimeter and 1 meter, but the microwave oven in your kitchen tends to use a wavelength of about 12 centimeters, which is about 5 inches. But wait, you might say, something's not adding up. You said that longer wavelengths have less energy, so why don't we cook our food with more energetic waves, like infrared or visible light? You can do that. It's called an easy bake oven. It does exactly that. It heats food using visible and infrared light produced by a light bulb. And you know what else? The oven in your kitchen that you use to store your pots and pans and occasionally use to bake cookies. It also cooks things using infrared and visible light. The heating element in an oven radiates light, which heats up everything in the oven. And this radiative heating, also helped by air heated up by the radiation, cooks the cookies. And yes, visible and infrared have more energy than microwaves, but they're also quickly absorbed by the food you're heating, meaning the outside cooks quickly and the inside cooks slowly. Microwaves aren't absorbed as easily, which leads to the first myth about microwaves listed on Wikipedia's list of common misconceptions. The myth is that microwaves cook food from the inside out. What actually happens is that microwaves penetrate up to 1 inch into the food instead of just heating the surface like stove or oven does. And this does lead to more even heating, but if the food is more than about 1 inch thick, then it'll block the middle from being heated as quickly as the rest of it. So it doesn't heat from the inside out. It just penetrates more deeply than an oven. Another microwave myth. Some people think that a microwave heats the water molecules in your food because of resonance, which is where waves reinforce each other to build up large vibrations, in exactly the same way your walls sometimes vibrate when you play loud music. I would explain more about resonance, except that it's not actually what happens in the microwave oven, so forget about it. Instead, it's polar bears. And by that I mean that some molecules have a part with a positive charge and another part with a negative charge, which is called being polar. Electromagnetic waves cause polar molecules to flip back and forth, which generates heat. Since water molecules are very polar, that makes them generate heat more quickly than nonpolar molecules, which is probably where the rumor comes from. So water does absorb more microwaves than other molecules, but it's not because of resonance, it's because water is polar. 2 more microwave myths. First, microwaves don't reduce a food's nutritional value, and in some cases they might actually preserve the nutrients because you don't have to cook things as long. And lastly, very few microwaves actually escape the oven. Recall that the microwaves, the waves, are about 5 inches in wavelength. Since the metal grating on your microwave only has gaps much smaller than 5 inches, it traps almost all the microwaves inside. Alright, finally, radio waves. Radio waves are fat. FM radio waves have a wavelength of about 3 meters, and AM radio waves have a wavelength of between 200 and 500 meters. These bands are regulated by governments to make sure your communication signals don't get contaminated with noise. Some other radio signals include TV broadcasts and mobile phones, which are also in the 1 to 10 meter range. These waves all pass straight through your body without you ever noticing they're there. There are all sorts of waves all around you, passing through your body all the time, and your body doesn't even care. It's kind of crazy to think about. Okay, now that we've run the whole gamut, let's go back to visible light. There are so many interesting facts about light, I'm going to try to speed through them to be able to cover my favorites, starting with color vision and cameras, then infrared and ultraviolet, then moving on to why the sky is blue and why plants are green. First, your eyes have 4 different types of sensors for light: rods that see black and white, and 3 types of cones that see color. Cones see color. One sees red, one sees green, one sees blue. By contrast, a camera only has one type of silicon-based sensor. They see color by putting a filter over some of the sensors so only one color of light gets through. So if you ever complain about how a camera can never capture the true colors of a scene, it's because the camera doesn't have the same sensors as your eye, and it actually can't capture the scene in the same way your eye can. Or it might be because you don't know how to use a camera. That's also a possibility. Interestingly, the sensors in a digital camera can see some wavelengths of infrared light that are invisible to humans, though the camera usually filters it out so the picture doesn't look washed out. But security cameras use it to their advantage. Some security cameras emit infrared light that is invisible to humans but clearly visible to the camera. That means even if it looks completely dark to you, to the camera it's like you have a bright light shining on you, which makes you perfectly visible. So keep that in mind next time you have a need to sneak past security cameras in the middle of the night. For ethical reasons, of course. Next light fact. You would be able to see slightly into the ultraviolet range, but the lens of your eye filters it out so your eyes don't get damaged. According to one guy on the internet who had a surgery to remove the lens of his eye to fix a cataract, ultraviolet light just looks like a dim purple. Okay, time for the big one. Why is the sky blue? Here's a hint. If we had no atmosphere, the sky would be black and you could see the stars during the day if you shaded your eyes. But we do have an atmosphere, and that means no stars in the daytime. It's all those pesky air molecules. When light finds a molecule, it makes the electrons in it start wiggling, and the molecule absorbs some of the light. But it doesn't hold on to it for long. The wiggling charges produce light, generally the same color as the light that was absorbed, and release it in a new direction. This is called Rayleigh scattering. So that's why the sky isn't black. Light from the sun gets scattered, and some of that bounces into your eyes. That's also why the sky is still bright for a short time after the sun is set. The sky is still scattering light from the sun, and the light is still hitting your eyes. But then, why is the sky blue? Why isn't it red or purple? Well, longer wavelengths of light, that means blue and violet, get scattered more. This has to do with the size of air molecules. Air molecules are much smaller than the wavelength of visible light, but closer in size to blue and purple than to red. And because they're closer in size, it causes more resonance and makes blue light get scattered more. Which means that if you look at a random section of the sky, it'll have more blue because the blue is scattered more. But if you look straight at the sun, it'll have less blue because the blue is scattered away more. It's like the blue is sucked out. That's why, even though sunlight is white, the sun looks yellow if you look right at it. But don't look right at it. That makes you blind. And I'm not joking. Sir Isaac Newton did an experiment where he stared at the reflection of the sun in a mirror, and he hurt his eyes so bad that he shut himself in a dark room for 3 days. Don't be like Newton. So now you know why the sky isn't red or green. But why blue and not purple? Violet light gets scattered even more than blue light, so shouldn't the sky really look purple? Yes. Except it's not purple, which means we're missing something. There are actually 2 reasons the sky doesn't look purple. The first is that our eyes are more sensitive to blue than to purple, so that's part of it. The other part is that the sun gives off more blue light than purple light. It turns out that not all colors are created equal, and the wavelength of light the sun gives off most is actually green. So if you've ever heard that our sun is a yellow dwarf star, that's a little bit of a misnomer. The sun's light is white, but if all the different wavelengths had to battle, green would win. Oh, so that's why plants are green, right? Because they absorb sunlight for photosynthesis, and that's where the strongest wavelengths of sunlight are? You fool, you've fallen for one of the classic blunders. Plants look green because they reflect the green light instead of absorbing it. The green light is wasted. They just spit it out. Why would they do such a thing? It's so terribly inefficient. Actually, they do absorb quite a bit of green light, but there's a reason for why they wouldn't want to take all of it. According to a paper published in 2016, plants don't just try to take in all the light they can, because too much light can damage them. Instead, They're adapted to take in a consistent amount of light. They would rather be reliable than super efficient. That lets them avoid getting burned. The environment is very noisy, with clouds, leaves getting in the way, day and night, and so on. By rejecting the green light, which can sometimes be too intense for them, it makes them better able to deal with these changes without getting burned. If this theory is true, and it seems likely, then that means on a different planet whose sun emits mostly red light, the plants would probably evolve to be red instead of green. That would look so cool. Alright, lightning round for light facts. Purple and violet are not the same color. Violet is a wavelength of light shorter than blue. Purple is a mixture of red and blue light instead of a single wavelength. So violet is in the rainbow, purple is not. In England, there's a law that says if someone has received natural light in their building for more than 20 years, they can forbid the construction of buildings that would block their light. The color brown is really just a very dark orange. Rods, the black and white receptors in your eye, are much better at seeing in the dark than cones, the color receptors. But strangely, rods don't pick up red light at all. It's out of their range. So astronomers who are trying to preserve their night vision can use red light without fear. This also used to be used by Navy vessels. The ship's captain's instruments would have red light to preserve his night vision. But this is no longer considered best practice because it makes it too hard to read the charts. And that's it. I'm going to end with a joke. I just read a book about electromagnetic radiation. It was light reading. Get it? Because light is a form of electromagnetic radiation? Oh, you got it without me having to explain? Well, anyway. Light is a waving electric and magnetic field. Microwaves and X-rays are the same thing, but with a different wavelength. Ovens cook things using infrared and visible light. Phone and TV signals use radio waves to send information, and the sky is blue because blue light is scattered more than other colors. Those were the highlights of this episode. I hope you found this discussion enlightening. Okay, normally this is the part where I mention what topic will be for next time, but I'm still deciding between a couple different topics, so I guess you'll have to wait and see. Peace. This has been Ideas Worth Exploring by Mark McDonald.